Okay, I want to review some of the basic ideas that we've already talked about for analyzing circuits. Now, we've looked at how to combine and analyze capacitors in series and in parallel, and we've also done the same thing with resistors. And that's really what I want to look at today is dealing with these resistive circuits, because that was really the last thing that we covered before the break, and I just wanted to review that to make sure that we're all solid with that. Okay, so we know that when we're dealing with resistors, the fundamental equation is Ohm's law. V is equal to IR, where V is the voltage drop across the resistor, I is the current going through the resistor, and R is the resistance of the resistor. Now, if we're talking about the resistance of a wire, we know that the resistance R is equal to rho, the resistivity, times the length of the wire, divided by the cross-sectional area of the wire. So if the wire is shaped like a cylinder and the area is a circle, then you would use pi r squared for the area. If it was a rectangular cross-section of a wire, you would use length times width to get the area, that sort of thing. And I want to remind you that the resistivity of a wire depends on temperature, where rho is equal to some rho naught, where that's a reference resistivity, times 1 plus alpha delta T, where alpha is another constant, something that you would look up on the internet or in a table somewhere, and delta T is the temperature difference. And so this gives us the variation of resistivity with temperature. And of course, I could plug that rho into there, and I could simplify that for an expression of how R varies with temperature. And we've already seen this in class, but we know that R is equal to some R naught, a reference resistance, that is a resistance at a particular temperature, times 1 plus alpha delta T. And that gives us how resistance varies with temperature. And of course, once we know the resistance, we can plug it into Ohm's law and solve for either the current or the voltage, depending on what we're looking for. Now, one thing that I want to mention is that when you are plugging areas into that formula, you have to be very careful about your units. When you look up the value of rho, it's going to give you units something like ohms times meters or ohms times centimeters. And you want to make sure that your length units are always going to be the same. And so if your rho is in ohms times meters, your area needs to be in meters squared. If your rho is in ohms times centimeters, your area needs to be in centimeters squared. And if you don't already have it that way, you need to do a conversion. And I just wanted to quickly review how to do that kind of conversion. So let's say we have a square and it is 1 meter by 1 meter. Obviously, the area of that square is going to be 1 meter times 1 meter, length times width, or that would be just 1 meter squared, which we can distribute the square, and that becomes 1 meter squared. Now, if I instead write it in terms of centimeters, we know that the area is going to be 100 centimeters times 100 centimeters, or 100 centimeters squared, and that works out to be 10,000 centimeters squared. And so the conversion factor from meter squared to centimeter squared is not 100, it's 10,000. And of course, this kind of approach will work if you need to convert centimeters to millimeters, or millimeters to meters, or actually millimeter squared to meter squared. Whatever your area conversion is that you want to do, this approach will let you handle it. And of course, Google will also do these kinds of conversions for you. And I don't recommend you rely on Google, but it can be a nice check to make sure that you've done your math right. Now let's consider resistors in series. We know that for resistors in series, whatever current travels through this circuit, if it passes through one resistor, it has to travel through the other resistor. There's no fork in the circuit. There's nowhere for the current to go. And so for when you have resistors that are connected in series, that's how you tell. There's nowhere else for the current to go. It can't fork anywhere. And we also know that that means that resistors in series see the same current. Now, if you're considering resistors in parallel, we know these resistors are connected in parallel because they have a direct link to the battery. This side of the resistor is connected to the negative terminal. This side of the resistor is connected to the negative terminal. There's a direct connection, and so whatever the voltage is of this terminal, that'll be the voltage of that side of that resistor as well as that side of the other resistor. Now, whatever the voltage is on the positive terminal, that's going to be the voltage on this side of R1 as well as the voltage on that side of R2. So when you have resistors that are connected in parallel, they see the same voltage difference, the same voltage. The same voltage. And that is, of course, for resistors in parallel. And if you need to pause that and write any of that down, you can, but it is in your notes. Now, one other thing that I'll just mention real quick is that if you look at the current does have the option to fork. So some of the current's going to go through R1, some of the current's going to go through R2. That's a clear indication also that your resistors are in parallel. There's a fork in the current. And so these guys can see different currents, but the voltages must be the same. And when we're looking at both series and parallel resistances, you'll remember that we often have circuits that have multiple resistors in them, and we want to be able to combine them. Specifically, we want to look at being able to combine series circuits and parallel circuits, or series combinations of resistors and parallel combinations of resistors. And the formula we use for that, for series, the total resistance is just simply the sum of the individual resistances, plus R2 plus R3 plus as many as you have. And so that will give you for resistors in series. And if we're looking for resistors in parallel, we know it's the reciprocals that add. So that is 1 over the total resistance of a combination of parallel resistors would be 1 over R1 plus 1 over R2 plus however many you have connected. And that is the way to combine resistors that are connected in parallel. Now, just to remind you, the common mistake that students often make is they'll add up all these reciprocals, but then they'll forget to flip their answer. So don't forget to flip that reciprocal at the end. So here's an example we can work really quickly. And you have other examples in your notes from when we covered this topic before. And I think that this should be pretty straightforward, but let's just go through it, and this will be a bit of a review. And it will help you on some of the mastering physics that you have assigned this week for these topics. So how do we analyze this circuit? What's in series, what's in parallel? Now you might look at R1 and R2 and you might think to combine them that they're in parallel. But what really strikes me, and that wouldn't be wrong by the way, but what really strikes me is that whatever current comes out of this junction and goes through R3, that same current goes through R4. And so immediately it just leaps out to me that R3 and R4 are in series. And once I see one that I know for sure, I like to just go ahead and combine them and draw a new circuit. And so if I combine R3 and R4 together, I would get a circuit that looks something like that. And so I've combined the first circuit, I've combined those guys together, and I end up with this as my new circuit. And I can really quickly calculate what R3, 4 has to be, because we know that R3, 4 is going to be R3 plus R4. And if we look over here, we know R3 is 150 ohms, R4 is 50 ohms. So if we add those guys together, we get 200 ohms. And so once I have those circuits drawn, I can look at R1, R2, and R34, and I can see all three of these are clearly connected in parallel now. And so I can do this combination all at once. And so if I combine all three of these resistors into one complete circuit, I know that 1 over RT, because these are in parallel, is going to be 1 over R1 plus 1 over R2 plus 1 over R34. And when you plug in the different values for R and you solve for RT, don't forget you have to flip that reciprocal at the end, you get that R total is equal to 50 ohms. Again, you just plug those numbers in, get a common denominator, add them, flip them, and it reduces to 50 ohms, and that is the total resistance of the circuit. Now, I've summarized those values in this chart here. Remember, we know the battery is 10 volts, and we were given the values of R1, 2, 3, and 4, and we calculated R3, 4, and the total resistance, and we made this table. And so what we did was we reduced this into a single equivalent resistance of 50 ohms and 10 volts. And so if I know that this is going to be 10 volts there, so I can add in here that that's going to be 10 volts for the total resistance circuit, and I can say that V is equal to IR, or I is equal to V over R, and I can plug in that the voltage is 10 volts and divide that by the total resistance of 50 ohms, and that gives me a current of about 0.2 amps. 0.2 amps. And then I, of course, can put that into my table here, 0.2 amps. And so now I've solved the entire single resistor circuit where I've reduced all of these resistors to a single equivalent resistance, and I now know the total resistance, the voltage, and the current. So what do? You go back to the previous circuit. So I've drawn the previous circuit where I had R1, R2, and R34, and these are resistors that are connected in parallel. And so we know that resistors in parallel see the same voltage. And so that 10 volts is going to be the same for R1, R2, and R34. So I can plug 10 volts into R1, R2, and R34, and that lets me solve for the currents in those slots as well. And when I apply Ohm's law, V is equal to IR, and I solve for the current, I is equal to V over R, I can solve for these currents, and so for R34, I get 10 divided by 200, and that gives me 0.05. And when I solve for R2, I get, again, we have 200, so that's 0.05. And when I solve for R1, that gives me 0.10. And so my currents are solved for those resistances. And note, we have the current comes in, and the total current that we have is 0.2, and that total current comes in and it splits into 1, it splits into 2, and it splits into 3, 4. So all of those individual currents should add up and give me 0.2. And so I've got 0.1 plus 0.05 plus 0.05. That gives me 0.2. I have that built-in check. You always want to look at your built-in check because it'll tell you if you made a mistake. Now, finally, we can go back from here to the original circuit. And the change that we make is R34 is uncompressed, and it's connected in series. And we know that for resistors in series, the current is going to be the same. So the current here is going to be 0.05 for each of these guys. And we can, again, simply apply Ohm's law. And when we do, we get that the voltages are 7.5 volts and 2.5 volts, simply plugging in V equals to IR. And that gives me the voltages across all of the resistors. And note, these voltages of R3 and R4, those drops need to add up to be 10 volts, because we know there is a 10 volt drop between R3 and R4, or R3, R4. So if I add together 7.5 volts and 2.5 volts, I get 10 volts, which is, again, that built-in check. Now, you have some examples like this in your notes. Look back at them, and hopefully these hints will help you with some of the mastering physics that you have assigned this week.